talking through the mechanical design of our robot. Our design is split up into two main subsystems, the drive subsystem and the package delivery subsystem, which are connected with T-slot alley extrusion. Alley extrusion was chosen as its lightweight while providing strength and ease of assembly. The drive subsystem consists of mounts for our ultrasonic sensors, limit switch, motor controller, Raspberry Pi, motors and batteries. The ultrasonics are mounted on Veriboard to allow for easy swapping of components if anything is damaged. They also contain various mounting points to allow for on-the-fly changes to the angle of these sensors. The limit switch is mounted to the front of the drive subsystem to be used for localization. This is slid into the alley extrusion and can be moved backwards and forwards to calibrate the correct position of the limit switch. All the other components are mounted directly to the 10mm laser cut acrylic base through M3 standoffs threaded directly into the base. As we are maximizing the area to hold packages, we opted to mount the motor within the roller. The motor is attached to this M8 bolt and connected with these two nuts. The nuts also contain spring washers to ensure that the motor does not come loose. The motor interfaces with the roller with the D shaft, allowing the roller to move around the motor while the motor stays fixed in place. The conveyor belt is made of a canvas sheet that is slightly elastic, allowing the belt to stay tensioned. The belt is driven by rollers that are covered in grip tape. This ensures that there's no slipping between the belt and the rollers. Slots have also been machined into the side of the alley extrusion. This ensures that when assembling, you can move the two rollers away from each other, and once the desired tension is reached on the belt, you can lock the two rollers into place.
In this section, I'll be discussing details about the Wombot's movement. Navigation for the Wombot is a simple combination of turn and drive. From its starting location, the robot will first turn to face its goal, then drive towards it. It will continue this procedure until the robot is within its desired positional accuracy range required by the user. Due to the motors not stopping rotation instantly, some positional and rotational inaccuracies were created. To counter this, the robot performed decreasing length of time drives to dial in to its goal pose. Using this method, the Wombot is able to achieve high precision drives between waypoints. As any two motors will have slight differences, some form of PID control had to be implemented to synchronize the speeds of the motors. A simple proportional controller was developed to decrease the speed of the leading motor until the number of rotations of the two motors were equal. To ensure the robot positional error doesn't increase as time goes on, the Wombot relocalizes to both the wall it deposits parcels on and the corner in the pickup zone. Each time it relocalizes, its positional error resets to 0.
For package delivery, the Wombot utilizes ultrasonic sensors to determine the package ID and deposit locations. This is accomplished through the pre-positioning of packages onto the conveyor belt into its designated zones, for the ultrasonics to read its distance and determine the deposit bin. This method proved to be more robust, cost-effective, and easy to operate when compared with the initial design of implementing a color sensor for package detection instead. The ultrasonic sensors solved all the issues that came with the color sensor when implemented. There was no more sensitivity to light, it was easily operated as there was no more need for calibration script, and finally, the ultrasonic was also significantly cheaper as it only cost a quarter the price of a color sensor. So once the package has been successfully identified, the robot begins its delivery to the identified package's assigned bin. When it reaches the bin, the conveyor will start turning until it detects either a new package or no packages, which will then either drive to the next bin or return home to be loaded up with new packages for the next cycle of deposits. This implementation allows the Wombot to deliver to multiple different bins in one cycle without having the need to return home. Overall, the package delivery system of the Wombot is robust to changing settings, easily operated by anyone, cheaper, and also efficient at delivering multiple packages to designated bins.
The next section that we will be discussing is the obstacle detection system. This is the failsafe that we implemented to ensure that if our communications with the other robot runs into problems mid-operation, such as having delays, we can keep ourselves and the packet safe by preventing collisions. The way that this algorithm works is, ideally our communication system, the path planning algorithm, would ensure that our paths do not intersect. Both the robots would always have waypoints at least 5 centimeters apart, accounting for the size of course. However, in the case where they get within 5 centimeters of each other and collision seems inevitable, any one of the ultrasonic sensors could detect this decrease in distance and our robot will be set to stop for 5 seconds. This helps us have enough time to reestablish communications between the robots and also replan the path.
Hello everyone, my name is Kelvin and I'll be talking to you about how we have implemented the communication system on the Wombat. In our case, there will be 2 robots in the arena that are trying to work together to complete the common task. To improve the efficiency, it is essential that we are able to communicate with each other. Our communication strategy is to use socket programming. Socket programming connects 2 sockets, a client socket and a server socket, and allows them to communicate bidirectionally in real time. In order to do this, we use the socket library in Python. The server program listens and handles incoming requests and connections, whilst the client connects to the server to send and receive data. We simply have 2 Python scripts created, one for the sender and one for the receiver, that can be used simultaneously. Given that both robots are connected to the same network, we will be able to establish a real-time connection and communicate using the TCP protocol. In conclusion, the Wombat is a robot that is self-sufficient, extremely effective in doing the job that it was designed for, that is to deliver packages. We hope you had a good time watching our presentation and thank you so much for listening.